Hi guys, Sajjad Hussain again with a new video. Actually this is not a new video, this is in continuation with my last video. In that video I took an example, and that example was example number 3 from a guide based on ASCE 702. This example was a 100 feet by 200 feet building which was 160 feet high. This building was used as an office building. In my last video, I calculated the wind load on main wind force resisting system. Now in this video, I am going to calculate the wind load on component and cladding. As you can see, the cladding for this building is defined here. That the mullions for glazing panels span 11 feet between floor slabs and mullion spacing is 5 feet. So this gives us information. It gives the information that the cladding is of glazing panels, that means it's made of glass, and these glass panels are 5 feet wide and they are 11 feet high. So based on this information, the wind load for the cladding is calculated. Now if we go to that portion which is here, the internal pressure coefficient for component and cladding, it is said that this building is a hurricane prone region. So the location is in a hurricane prone region, and the glazing is assumed not to be debris resistant. So this is very important, that it cannot resist the debris which will be generated in case of hurricane. And the glazing is considered as openings, and this is a very standard statement that whenever a building is cladded with glaze panels, so this building is treated as an open building, or these glazings are treated as open openings, and this building is considered as partially open building. That's why this building is classified as partially enclosed building. So for main wind resistance frames, the pressure is calculated like this, where the coefficient of G and CPI was calculated like plus minus 0.55. Here I want to show you that the negative internal pressure is taken as minus 55, and it is multiplied by an internal pressure by the QH, which is 35.1, and when we see 35.1 is a pressure at the highest point, that is at 157 feet high, the QH is equals to 35.1. So this internal pressure is calculated by multiplication of the GCPI coefficient and 35.1 QH. But for positive internal pressure, the GCPI is taken as 0.55, but the QH is taken as 30, where it is mentioned as QZ is gained by interpolation at height Z, which is equals to 90 feet. Why 90 feet? It is explained over here. The QZ will be evaluated at 90 feet for positive internal pressure. That means 30 feet above height of surrounding buildings in 1500 feet radius. See section 6.2.9.3 of the standard. This section is in ASCE 702. Now the similar section is reproduced or renumbered in ASCE 716 as section 12.3.1. The section 26.12 is enclosure classification, and section 26.12.2 deals with openings, and 26.12.3 deals with protection of glazed openings. Now this is our concern, and here in 26.12.3.1 it is the wind-borne debris region. So here there is a specific condition. It says that the glazed opening shall be protected in accordance with section 26.12.3.2 and the following locations. So these locations are there, but then there is an exception. This exception says that the glazing located more than 60 feet, in our case it is 160 feet, above the ground and more than 30 feet above aggregate surfaced roofs, including roofs with gravel or stone blast, located within 1500 feet of the buildings shall be permitted to be unprotected. And it was mentioned somewhere in this example that the surrounding buildings are 60 feet high. So we added 30 feet to the 60 feet and this becomes 90 feet. That's why here you can see that QZ is gained by interpolation at a height of 90 feet. And that's why it is said over here that 30 feet above height of surrounding buildings in 1500 feet radius. So it is clear that in the surrounding there are buildings which are 60 feet high. So we have added 30 plus 60 is 90. So we are taking the pressure we are taking the QZ value of 90 feet to calculate the positive internal pressure. Now based on this, I performed my calculation. I reproduce over here and I summarize all the information over here, that mullions of glazing panels span 11 feet between floor slabs, and mullion spacing, there should be a full stop, and mullion spacing is 5 feet. Glazing panels are 5 feet by 5 feet by 5 feet 6 inch high, typical. They are not resistant to wind-borne debris impact. Also, there are buildings up to 60 feet in height located within 1500 feet radius. So based on all this information, we calculated the wind force on component and cladding. So let us go to that portion, component and cladding, and I'll show you how I have calculated the wind force on component and cladding. Of course, in last video I explained that I took the data from ATC website, and the wind speed for the risk category 2 was 136 miles per hour. Based on that, I calculated first the main wind force resisting system wind loads. In this Excel sheet, all the calculations were done, and I also calculated the gust factor, that was 0.858. Then I calculated the wind load on parapet wall, and the wind load is calculated like this. Now I added wind load on component and cladding, that means first wall. And I took from chapter 30 part 3 buildings with height which is greater than 60 feet. So this part 3 is applicable for this case, as it is mentioned in part 3 that use part 3 of chapter 30 for determining the wind pressure for component cladding of enclosed and partially enclosed buildings with H greater than 60 feet or 18.3 meter that have roof shapes as is specified in the applicable figures. These provisions are based on the directional pressure with wind pressure calculated from the specified equation applicable to each building surface. So that portion was done. Now for component and cladding, let me show you chapter 30 part 3. Let us go to chapter 30. Part 1, Part 2, here is part 3. At part 3, this part is applicable for buildings which are higher than 60 feet. So it is clearly mentioned that use this part 3 for determining the wind pressure for component cladding of enclosed and partially enclosed buildings with height greater than 60 feet and that have roof shapes as specified in the applicable figures. So building types, of course it is repeated here, and it is said that for component cladding of building type as shown in figure 30.5, and the equation is the same as P is equals to Q times GCP minus QI into GCPI. So we will see when we go to table 35.5, which is part of the figure explained over here, figure 35.1. So here is the steps mentioned for wind load calculation as per part 3, and of course the step 1 is the establishment of the risk category, then velocity as I explained, then the parameters like KD, exposure, KZ, KE, enclosure, just we read, and the GCPI values, all this. Then we have to define KZ or KH, that is based on table 26.10.1. Then we have to calculate the velocity pressure, then external pressure coefficient GCPI, and this should be calculated for the walls as figure 30.5-1, roof, etc. And then you have to calculate the pressure. Then you have to follow that. I should show here. This is figure 30.5.1, components and cladding, part 3, for H is equals to greater than 60 feet, external pressure coefficients for enclosed and partially enclosed buildings. This is for wall and roofs. So here is the condition. Wall elevation is given, where zone 5, zone 4, they are defined over here, and the coefficients are taken from this graph. As per this area, we took the coefficient from here. So based on all this information, what I did, I calculated the wind pressure for component cladding. This is the reproduction of the same section. Now, component and cladding wall pressure. These are not CMU wall, these are glazed panel are supported like this. Similarly here, glazed panel effective area is like this. So this definition of the effective wind area is here. We also know that the width of the mullions was 5 feet. So effective area for the mullion, this will be maximum of h into h by 3 or h into b, so it comes out to be 55 feet square. External pressure coefficient, it can be taken from here. So if it is 50, 55 will be somewhere here. We can draw a line somewhere here, and then we can calculate the external pressure coefficient GCP. So based on that, I did all this exercise. And I calculated the coefficients from here. Let me show you the calculation. So here are my here is the calculation sheet. So based on all, the coefficient for panel, it is taken as 0.87. For glazing panel itself, the area comes out to be 27.5. So the coefficient is 0.87. 0.87. This is for positive and negative pressure, and this is for negative pressure in zone 5, and the velocity comes out to be like this. This is velocity at 60, this is velocity at 90. So all these values are tabulated over here. Like I calculated height, kz, qz, and in zone 4 all these values are calculated like this. Negative value will be at 90 feet high. Similarly in zone 5, and these are the internal pressures. So based on that, I calculated all this, and here this is the net sum. Because you can see I have already added the positive and negative pressures. So this is the final pressure in zone 4. This is the final pressure in zone 5. This is the negative pressure, and this is the negative pressure in zone 5. These are already added over here. So the same thing, I copied the same table over here. So this is the way the wind pressure on the glaze panel should be calculated. This is for the mullions and this is for the panels. The panel has a different dimension size, so their coefficients were a little bit different. So I calculated all this over here. The same table, the same figure is used for panels. The panels are 27.5 square feet and the mullions are 55 square feet. So all these values are there and I calculated all these values. So once we calculated the wind pressure on component and cladding, of course we should calculate in both the directions. Then we should design the component and cladding accordingly. That means it's not only important that you calculate the wind force on the main wind resisting frame system. That's fine. But at the same time, if there are panels, there are components cladding, then you have to calculate the wind force on the components and cladding according to the ASCE 716 procedure. Then your cladding should withstand this pressure. That means you have to ask your manufacturer that please make sure that the panel should meet this pressure. That means the thickness of the panel should be ensured by the manufacturer that this should withstand the pressure. So hopefully this will summarize the complete wind load definition for a building of 160 feet high, which is cladded by glazed panels. So thank you very much. Hopefully you will like and subscribe my channel. Thanks again. Bye. One more thing I forgot to mention. I developed two Excel sheets. One is component and cladding for mullions. Here are the coefficients for mullion, which I took from the figure I showed before, and then this worksheet, it shows the component and cladding for panels. So there are two different things, panels and mullions. So two different values are computed. That's why I showed you two different tables. One for the component and cladding of the mullions, and one for the component and cladding for the panels. These calculations, they are based on the coefficients calculated here. For mullions, the coefficients are a bit different, and for panels, the coefficients are different. So hopefully it is now clear. Thank you very much.